Characteristics of equilibrium constant. We have already discussed what is Kc and what is Kp. Kc is equilibrium constant in terms of active masses. Kp is equilibrium constant in terms of partial pressures. Similarly, what are the factors on which K depends? The numerical value of equilibrium constant K is independent of the following factors. 1. Initial concentrations of the reactants and products. What do you mean by this? Consider a simple example of reversible reaction, hydrogen reacting with iodine to give hydrogen iodide. When we carry out this system in a closed vessel by taking 1 mole of hydrogen and 1 mole of iodine at 444 degrees centigrade, when equilibrium is attained, let us calculate the value of K, and let the experiment be repeated by taking 2 moles of hydrogen and 5 moles of iodine, and again at 444 degrees centigrade in the same vessel, let the system attain equilibrium and find the numerical value of K. We find the K in both the cases is same. Even if the system is carried out by taking 2 moles of hydrogen, 5 moles of iodine and 50 moles of HI in the same vessel at same temperature of 444 degrees centigrade, and let the system again attain equilibrium and find out the numerical value of K. We find the same value for K. As long as the initial concentrations of reactants and products are taken into account, the numerical value of K remains constant. The presence of a catalyst. Let us take an example of nitrogen gas reacting with hydrogen gas being carried out in a closed vessel. Let this system attain equilibrium state at a temperature of 450 degrees centigrade and find out the numerical value of equilibrium constant K. Let the experiment be repeated by allowing the system to attain the equilibrium by using the catalyst and find once again the numerical value of K. We find the numerical value of K is same in both the cases. In other words, when the system attains the equilibrium without the presence of catalyst, the value of K is found to be the same when the same system is allowed to attain the equilibrium in the presence of catalyst. So the presence of catalyst does not affect the numerical value of equilibrium constant. Third factor, the direction from which the equilibrium has been attained. That is, when the system is allowed to attain the equilibrium from left hand side to right hand side, or when the system attains the equilibrium from right hand direction to left hand direction, the numerical value of the K does not change. That is, the numerical value of K is independent of system attaining the equilibrium from either of the directions. The fourth, the presence of inert materials. What do you mean by the system attaining the equilibrium when inert material is added? Inert material is the one which, when added to the system, neither react with any of the reactants nor react with any of the products. Thereby, even when inert materials are added to the system, when equilibrium is attained, the numerical value of the equilibrium constant remains same and does not depend on what inert materials are added. Thus, K does not depend on the addition of inert materials. Let us now discuss on what factors the numerical value of K depends. The numerical value of K depends on mode of representation of the reversible system. What is the meaning of this mode of representation of the reversible reaction? Let us take an example of a reversible system A reacting with B to give C and D. The Kc can be written as active mass of C into active mass of D by active mass of A into B, equation 1. Now let this same system be allowed to proceed in the reverse direction. That is, the substance C is allowed to react with D to give A and B. This system is the reverse of A plus B giving C plus D. But what is the equilibrium constant K dash C for this system? K dash C is equal to active mass of A into active mass of B by active mass of C and D. That is 2. Let us now see how this K dash C, the equilibrium constant for the reversible system of the first, is related to Kc. We find that K dash C is equal to 1 by Kc. In other words, the equilibrium constant for the reverse of the reversible system is the reciprocal of the first. Thus, if for the system A plus B giving C plus D, if Kc is 100, what is K dash C when the same system is allowed to proceed in the reverse direction? It is 1 by 100. Thus, when a reversible reaction is allowed to proceed in the reversible direction, that is, we are changing the system entirely opposite of the first system, then the numerical value of K is the reciprocal of the first. Let us now take another example of a reversible system where when nitrogen dioxide is subjected to thermal decomposition, it gives nitrogen and oxygen, that is 2NO2 giving N2 plus 2O2, for which Kc can be written as molar concentration of nitrogen into molar concentration of oxygen to the power of 2 by molar concentration of NO2 to the power of 2. Equation 1. Let us now take the stoichiometric form of this system 2NO2 giving N2 plus 2O2 by dividing with 2. On dividing this system with 2, we get NO2 on heating gives half N2 plus O2. What is the equilibrium constant for the above reversible system? K dash C. That can be written as K dash C is equal to N2 whole to the power of half into O2 whole to the power of 1 by NO2. Equation 2. Now tell me how K dash C is related to Kc. K dash C is related to Kc as K dash C is equal to root of Kc. Is it true? Compare equations 1 and 2. What do you get? K dash C is equal to root Kc. What do you understand from this? That is, when a reversible system is divided by 2, the equilibrium constant for the new system is the square root of the equilibrium constant for the first system. Suppose if we get the new equilibrium system by dividing the first system with 3, then the equilibrium constant for the new system will become cube root of the first system. Now, if for the general system A plus B giving C plus D, Kc is active mass of C into active mass of D by active mass of A into active mass of B. If this system is divided by N, then the equilibrium constant for the new system K dash C obtained by dividing the first system with N will become equal to nth root of Kc. Is it true? Yes. A reacting with B to give C and D. For this system, Kc as usual can be written as molar concentration of C into molar concentration of D by molar concentration of A into molar concentration of B. Equation 1. Let this system be multiplied with N. That is, we are writing a new stoichiometric form of the first system. That is, N of A reacting with N of B to give N of C and N of D. What is the equilibrium constant K dash C for this new system? K dash C is equal to active mass of C to the power of N, active mass of D to the power of N by active mass of A to the power of N into active mass of B to the power of N. Equation 2. Now let us see what is the relation between K dash C and Kc. What do we find from this? K dash C is equal to Kc to the power of N. Let us take an example. Nitrogen gas is reacting with oxygen gas to give nitric oxide, for which the equilibrium constant is, say, Kc. Now what is the equilibrium constant if the system now is written as 2N2 reacting with 2O2 giving 4NO? If the equilibrium constant for this system is K dash C, how K dash C is related to Kc? Do you know the answer for it? K dash C is equal to Kc to the power of 2. It will become K dash C is equal to Kc to the power of N. Thus, when a reversible reaction is multiplied by N, thereby we get a new system, then the new value of K is K to the power of N.